All right, so yeah, so I did this work with Dr. Marge McShane. My name is Yvonne Leon with the Language Endowed Intelligent Agents Lab at RPI. The title of the paper is Language Generation for Broad Coverage Explainable Cognitive Systems. So this paper describes some key design features of the natural language generation capabilities that we've recently begun developing within the OntoAgent cognitive architecture at the Leia Lab. Natural language understanding in OntoAgent is described in the book Linguistics for the Age of AI by Drs. Marge McShane and Sergey Nirenberg. The book is open access, so if anybody would like access to it, I can provide it after my talk. And this paper answers the natural question, and what about natural language generation, or NLG? So this is a high-level view of the OntoAgent cognitive architecture. We call it content-centric because we primarily focus on building and teaching agents to independently learn the extensive knowledge about language and the world that they need in order to function in human-like ways. So the yellow box on the left shows NLU, and the box to the right shows NLG. And they both rely on the same exact knowledge bases and overall approach to computational cognitive modeling. So producing language can generally be separated into two primary tasks. The first being deciding what to say, and the second being deciding how to say it. The prerequisite for NLG is what we call content specification, which is deciding what meaning is to be conveyed. In applications, this is usually provided by agent reasoning. However, in the current state of the art, nearly all cognitive systems have very narrow coverage, and so they can provide very few content specifications. Our goal, by contrast, is to actually solve the problems of broad coverage natural language generation, including having microtheories for things like polysemy, paraphrase, co-reference resolution, and more. So the question, where will the content specification to foster such R&D come from is kind of an obvious question. And the answer is that our natural language understanding system provides much of these content specifications. So we use our NLU system to create ontologically grounded text meaning representations, which we call TMRs, to reflect the agent's understanding of input texts. Then we kind of automatically strip the metadata that indicates, for example, what words and senses in the lexicon were used to generate that meaning representation. And then these stripped meaning representations serve as the content specifications for our NLG development. And since the natural language understanding system can analyze open domain texts, that means that we actually have a lot of fodder in the wild for working on the difficult problems of NLG and to kind of help our development and research in that area. And so this is our architecture for our NLG system. And as I said earlier, it uses the exact same knowledge sources and situation model that our NLU system uses. And this paper describes our recent work on the first 4 stages, being lexical selection, converting candidate sets into candidate solutions, generating candidate sentences from those candidate solutions, and then finally selecting the best sentences, the best sentence from those candidate sentences. So the first stage, like I mentioned, is lexical selection, which is the process of collecting the lexical senses that might ultimately contribute to the generated sentence. And to give just a taste of why this is particularly difficult, words and phrases have syntactic and semantic requirements that are listed in our lexicon, and these must be fulfilled within their particular generated sentence. And so word senses can only combine into a sentence only if all of their needs are fulfilled by the other elements of the sentence. So this is an informal sketch of the verb fix, which means fasten. And syntactically, you can see that it requires a subject, a direct object, and a prepositional phrase with the word to. And semantically, it requires an agent, a theme, and a destination, all of whose fillers must match the semantic constraints specified in that ontological frame for fasten. So in short, there's a ton of constraints that we have to kind of keep track of and make sure that we're checking constantly. And so the previous step selected which lexical sentence could, in principle, combine into a valid sentence. This step of converting candidate sets into candidate solutions further prepares those candidate sets to be passed off to an engine that generates the actual English sentences. And it associates the selected words with an inventory of features that guide the generation process that are specified either in the previous lexical selection step or in the content specification that we call the TMR. And to generate the actual English sentences from this this highly specified fodder, we use a realization engine called Simple NLG, and it uses the features that we pass to it that I just mentioned to do things such as generate the correct morphological forms, create passive or imperative constructions if they're appropriate for the current context, and handle things like possessives as well as a significant number of other features. And so as regards selecting the best sentence from the candidates generated, we're currently investigating a few different avenues. Machine learning methods seem like they might be particularly useful for the scenario. After all, machine learning-based language models such as GPT-3, BERT, and Switch-C are all really, really great at generating smooth, natural-sounding texts. Unfortunately, no off-the-shelf models exist that work within our formalism or feature requirements at the moment. And since the core of the work is rooted in the knowledge-based methods of candidate generation, our candidate selection using machine learning methods has kind of been put on the back burner for now. And what we had hoped for is that we could kind of pass an off-the-shelf model a list of options for each of a sequence of sentences comprising a text and have it output the best sequence of sentences. And this would be particularly helpful with respect to, for example, selecting among synonyms that have no distinguishing features in our knowledge bases, things like realizing referring expressions, realizing the tense or aspect of verb forms, and capturing the topic comment structure of discourse, as well as a few others. For now, given that all the sentences produced by the previous steps are contextually and grammatically valid, we have actually chosen to just simply select any of the candidates for output, but further development for candidate selection, specifically using machine learning and integrating machine learning in this area is definitely on agenda. So let's just quickly go over an example. So this is what you see on the screen is a simplified text meaning representation for the sentence "Tom secures a painting to the wall." So as you can see, the instance frame for fasten provides the fillers for the slots of the semantic structure of the concept. And so the agent of the fasten event is the frame representing Tom, who is a human that the agent already has in its knowledge and episodic memory. And although the agent knows the name of the human is Tom, there are still many ways to realize this frame, including things like pronominalization or simply excluding the reference entirely from the sentence. So the theme of the fasten event is picture. And so by now, we pretty much already have the guts of what we want to say, that the human fastens a picture. And if we recall from the syntactic structure of the lexical sense from fix earlier, as well as the semantic structure, we know that we're still missing the prepositional phrase and the destination slot. So where should the human fasten the picture? And obviously the destination of the fasten event gives us that information, which is needed to fulfill the requirements of that verb fix. So now we know conceptually that the human fastens the picture to the wall. And each of the frames of the meaning representation corresponds to a set of lexical senses that evoke the meaning of that particular frame. And so these are a set of example sentences that could be produced from the previous TMR. And as you can see, virtually any of them are contextually relevant and valid, even though, as humans, we might say that one is preferable to another. So what about explainability? So this line of work enables agents to generate natural language from content specifications that explain agent behavior. And the nature of our knowledge bases and processing allows an agent to point directly to the knowledge and internal processes which generated a particular behavior. In this case, the behavior of generating a natural language sentence or multiple sentences. And so how does this work differ from the knowledge-based work on NLG that was carried out half a century ago and kind of proved to be so difficult that people virtually gave up on it? Honestly, none of the problems have really gone away, but our understanding of both the content, including theories of linguistics, cognitive modeling, and ontological reasoning, as well as our strategy have evolved. And as regards strategy, as I mentioned earlier, we focus on lifelong learning to overcome the so-called knowledge bottleneck and integrating language processing with other channels of perception and general reasoning, including things like visual reasoning or visual perception and things like proprioception. And so it's become clear at this point that AI won't reach its potential without explainability. So no matter how difficult it is to build these explainable systems, it really must remain on agenda. And so, like I mentioned earlier, the goal of this work is really to develop a natural language generation, the natural language generation capabilities for the content-centric cognitive architecture called OntoAgent. R&D is really still in the early stages for NLG, but this paper describes some of the core design features of our natural language generation system. And so our goal is really to solve some of the problems of broad coverage NLG, including many of the microtheories covered by our NLU system, and to bootstrap development of our NLG system with meaning representations from open domain texts. And I really didn't go into really any of the kind of nitty gritty of how this happens, but I would be happy to talk with y'all about this afterwards or in the 2-minute questions. Thank you all so much.
That's perfect timing. It's actually 10 minutes, 5 seconds. So any questions? You can either raise your question here or utilize the Slack channel on paper number 5.
And there will be breakout rooms after this session, so please use those as well.
If there's no other questions, Ivan, so this is a lexical framework with constraints on lexical items and how they fit together, which sounds very reminiscent of lexical functional grammar, head-driven phrase structure grammar. And although those were arguably less semantic, they did have some semantic features attached. So and I know they couldn't hook up to a knowledge base, right? But so is it in that spirit, but moving beyond it?
It is very much in that spirit. I think our group generally is focused on building knowledge bases, including ontological knowledge bases that kind of coincide with our lexical knowledge. So our lexical knowledge has kind of semantic components associated with it that allow us to constrain how we're using those either word senses or constructions and things like that. So yes, it is very much reminiscent of it. However, I think that we've kind of added some contributions in the way that we're thinking about ontological knowledge being used for reasoning. I primarily work within the kind of natural language generation part of our.
So I think what you're saying is HPSG and LFG would generate grammatical sentences, but they might not make sense in, say, a connected discourse. And I think that's worth highlighting next time you talk about this.
Okay, great. Thank you so much.